All right, let's go ahead and get started. I'd like to thank everyone who's joining us today. Welcome to today's CNCF webinar, Navigating the Service Mesh Ecosystem. I'm Karen Chu, Community PM at Microsoft and CNCF Ambassador, and I'll be moderating today's webinar. We'd like to welcome our presenter today. We have Lachie Evenson, Principal Program Manager at Azure and CNCF Ambassador. Just before we start, a few housekeeping items. During the webinar, you will not be able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop in your questions there and we will get through as many as we can at the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not put anything into the chat or ask questions that would be in violation of the Code of Conduct. Basically, please just be respectful of all your fellow participants and presenters. Please also note that the recording and slides will be posted later online at the CNCF page of at cncf.io/webinars. And with that, I will hand it over to Lachie to kick off today's presentation.
Wonderful. Thank you very much, Karen. Thank you for having me, CNCF. It's wonderful to be here today. I hope everybody's having a great day wherever you are dialing in from. Dialing in feels so antiquated, that term now. Nobody's dialing in anymore. I was told I was supposed to wear a hat, so I'm going to put on my, my proverbial ambassador hat now, and I will go ahead and share my slides, and then we can get straight into it. Excellent. Hopefully, can you see them, Karen? Excellent, fantastic. Okay, so today we are going to go on a journey navigating the service mesh ecosystem. So I wanted to kick off and get into what is a service mesh. We can't assume that everybody knows what a service mesh is. So I'm going to quote a friend of ours named William, the CEO of Buoyant, who are known for Linkerd in the CNCF ecosystem, which is a service mesh. But he states that a service mesh, and I quote, is a dedicated infrastructure layer for making service-to-service communication safe, fast, and reliable. And he also goes on to say, if you're building a cloud-native application, you need a service mesh. Now, there is lots to talk about in the service mesh ecosystem. In my experience with service meshes, you may not need them day one on your microservice journey, but you will eventually need them because they offer some really great platform enhancements so that your developer team doesn't have to worry about encryption or observability or getting metrics or access policies, building them into the applications. They can trust that the platform provides them. So we're going to go on a journey today and navigate these murky waters sometimes, hopefully to make them a little bit clearer. So stay with me. We do have demos. We're going to get into the weeds now. So let me start with Service Mesh Interface. So Service Mesh Interface was announced back at KubeCon EU in Barcelona in 2019. Have everybody who went think back to that wonderful moment under the sun in Barcelona. What a wonderful time. And I'm sure that next week at KubeCon EU is going to be a fantastic event. So I encourage everybody to participate and show up and engage in this new and wonderful format. But Service Mesh Interface was around defining a common set of interfaces that describe how you can interact with service meshes on Kubernetes. It's a basic feature set. So, some folks have said it's a least common denominator, and it is really just what do most users want to get out of service meshes? What's the most common features that are common across all implementations of service meshes that give the developer community and the user community what they need from that service mesh infrastructure. Service mesh interface should support new mesh capabilities over time, and we'll go into that. We'll share what service mesh interface covers now and what I think and what I've heard in the community might be the next set of interfaces that SMI might want to tackle. And a space for the ecosystem to innovate with mesh technology. What we were hearing when we were working on service mesh interfaces, having to decide on the implementation of the service mesh up front when I really don't know what it provides is really hard. And if I want to switch out service meshes or make changes or try out different platform specific features, it's hard to do that if I'm writing everything to an individual implementation. Now, if we think about other examples of this in the Kubernetes ecosystem, there is CRI, which is an abstraction for container runtimes, which has allowed container runtimes like Cryo, Containerd, and many other implementations of container runtimes to exist under a standardized API that can be plugged directly into Kubernetes. So you have that clean abstraction. Another example could be CSI, CNI. They are common abstractions that all network and storage providers support, and allow interoperability so that you can get the best out of the storage platforms that you need, or networking platforms, but have a common abstraction. So I don't like to think about it as least cost. I like to think about it as portability that allows everything to operate the same at that abstraction. And when you take a dependency on those APIs, you allow some portability. So let's go into what exactly that means. So the initial specification, what we heard from the community and those folks looking to turn to service mesh is, here are the top 3 features that we want from a service mesh. One is traffic policy. We want to be able to define service-to-service policies at layer 7. So if you think in Kubernetes, we have network policies, let's go up the stack to layer 7 and look at policy at the HTTP, RPC, gRPC level, and actually put service-to-service policy in. So we could say service A can talk to service B, but service A cannot talk to service C. And we can define that in policy to allow our microservices access to other microservices. And you can even get granular. I'll share some of that soon. Traffic telemetry. So there is this term, the golden metrics. How many, what's your error rate? How many queries per second? Those are great metrics that service owners really want to know how their services are performing. Bubble them up in a place where you can actually have access to them and start to build those statistics out of the platform itself. You can have that monitoring inbuilt into the service mesh. And finally, traffic management. So we've all heard about canaries, maybe. We've heard about continuous deployments, continuous rollouts, and tools like Flagger, which is a tool by the folks at Weave that actually allows progressive delivery, which means I have version 1 of service A and I want to push out version 2 of service A. How can I onboard traffic to service 2 and take all those inputs and metrics and determine whether service 2 is healthy? Sorry, version 2 is healthy, and route that traffic progressively onto that new version of that application, enabling things like Canary. So those were the top 3 asks that we heard, and Service Mesh Interface had APIs for each of them. Why does the ecosystem need SMI? I think, you know, it goes akin to something like CSI or CNI to have a provider agnostic way to interface into service meshes. So we're not worried about who implements the service mesh. We're worried about the features the service mesh provides and having a standardized API to interact with that, which allows portability, but allows you to make sure that there are other different options out there to create an ecosystem of service meshes. Kubernetes native. We wanted, with the rise of CRDs and extension API servers, we wanted it a way to be interfaced, integrated directly into Kubernetes so that you can use all the tools you know and love, like Kube Control and others, to interact with service meshes. So you don't need to go grab another set of tools to interact with SMI. You can just use Kubernetes. And things like custom resource definitions allowed that. Extensible, we expect, you know, there are more use cases coming over time. We started with those 3 APIs. How do we move to the next set of problems that are being solved of service meshes and create new common APIs in SMI? Examples I would cite that I've heard most commonly is multi-cluster capabilities for service meshes. So how to install a service mesh on discrete Kubernetes clusters and then connect them together. I've also heard circuit breaking. How can I actually stop traffic based on some metrics going to that service? And finally, traffic rate limiting. So if I can see how many queries per second in the load that's generating, how do I actually limit the traffic to that backend service? They are just some examples I've heard. It's certainly not exhaustive, but SMI allows for new APIs to be bubbled up as the innovation is happening in the community. So here's a look at what SMI is really doing. So down the bottom on the right, you see different service mesh implementations out there in the open source ecosystem. So we have Istio, Console, Linkerd, and more. Service mesh interface can be implemented either via an adapter or directly supported in the controllers themselves. For example, Linkerd. you can then put your apps, your tooling, and all the ecosystem of tools just to rely on service mesh interface, and they can program any of these service meshes under the hood. Now, to date, I think service mesh interface has been around for a little over a year, and there are 8 different service meshes that implement service mesh interface. That means if you have an app that's trying to do some traffic routing and you use SMI, it doesn't matter which of these 8 service meshes that implement that, you will have the same behavior. So here's the APIs. I mentioned 3. They're actually broken down into 4. There's the traffic access control. So we want to make sure that service A has access to service B, and using Kubernetes primitives to actually define what service A and what service B are. Traffic specifications. So we're looking at the protocols. What do the protocols look like? We can dig down into them. Are they matching on regexes in headers? Are we looking at different fields in the headers to match that traffic and then apply that access control? Traffic split, so direct percentages across n number of services. So think of it tallying up to 100%. If you have service A version 1 and service A version 2, you could say 50-50 and have the traffic round robin split 50-50 between them. Traffic metrics is for tools like dashboards, autoscalers, progressive delivery tools like Flagger, so that they can take the input from how are these services performing and actually make decisions about whether they continue the progressive rollout. So they are the 4 APIs that are in SMI today. And this SMI is actually a specification. So if you've never worked with specifications themselves, they are actually defining the fields and the values of these APIs. And then implementers who have service meshes can come and adopt different versions of these specifications and implement them into their specific service mesh implementation. So what we've got here is we have 0.5.0 of the specification, and then we have each of the components under there listed as we're iterated through, as more folks are using SMI and saying, here's things that I need to happen with SMI. So you can come and participate in these communities and help shape what these common abstractions look like. And we, obviously we hope to move them through alpha to beta as more implementations come and more users show up and say, these are the things I want from a service mesh. We should be able to move them through beta to stable would be the goal, and add additional APIs. So technically, what am I talking about here? You've heard a lot about what SMI is. Here's where the rubber meets the road. So you have a set of CRDs that can be installed at any cluster. So obviously we have one for those, each of those 4 APIs we've defined on the previous slides. We can use kube control to actually create custom resources of these custom resource definitions. And then there are controllers in the actual service meshes that look for those resources and then implement them at the data plane of the service mesh. The SMI providers run, I mentioned that just now. So we have basically controllers that are looking for these resources and then implementing. SMI also ships an SDK written in Go for easy implementation. So if you want to implement SMI into your service mesh and you're working on a service mesh, you can use the SDK to bring it into your code base and use it easily and quickly. There are other common components that are shipped under service mesh interface, like a standardized extension API for metrics that things like Linkerd have built out, and the wonderful folks over at Linkerd have been responsible for contributing that. Init containers, and then anything else that's common we can actually talk about and put in SMI. So if you think you have something that's common to all service meshes that you would like to share and have a common space, we'd invite you to make a proposal to SMI, and we can see about housing that under the SMI set of specifications and components. I want to call out the partnerships here that started SMI. So initially, we had the folks at Linkerd, HashiCorp, Solo, Red Hat, Rancher, Canonical, Docker, just to name a few. And these companies and folks from these companies have been instrumental in landing the initial implementations and actually proving out the specifications and versioning those specifications up. So I want to say thank you to them all, but it really was a cross-company effort to get SMI up and running and then actually have different service mesh providers implement it. You know, for example, the folks at Rancher have Rio, which implemented SMI under the hood, and they were able to do that without, you know, even showing up to a meeting. They could read the documentation, implement it, use the SDK, and away they went. Really, you know, that's a great outcome. So kudos to the folks over at the Rancher that worked on getting that into Rio. So if you want to interact with the SMI community, here's some links for you. Obviously, I haven't mentioned this yet, but SMI is actually a sandbox project under the CNCF. There's a website, smi-spec.io, if you'd like to learn more. Everything's housed under the following GitHub repo. The links are up there. And we invite you to take a look around those repos, join the SMI channel in the CNCF's Slack if you have any questions. And then you're welcome to come and join the meeting. There's a communications link there as well. This will all be in the recording, and the deck will be shared also. So you don't worry too much about screenshotting those links now. You can get them afterwards. So that's how you can get involved. And finally, just to put a bow on, you know, SMI here, the goal of SMI was to provide a portable set of APIs that were provider agnostic and allow tools and integrators and implementers of service meshes to be able to offer higher level services. An example of that is Flagger. I've mentioned that before. We've even had conversations with the open source team at Kiali being interested in implementing SMI metrics so that Kiali could be portable across many service mesh implementations. And we want to make sure it iterates over time. So as the folks working on service meshes and the user community is finding new platform implementations and features, we can actually bubble them up into SMI. SMI itself is not a service mesh. It doesn't ship a service mesh. And you know, we don't require implementations of APIs. So if you want to just take traffic split, you have a service mesh or some tool that needs service mesh-like features, you can implement just traffic split. So in order to conform with SMI, you don't need to implement it in its entirety. And, you know, we don't want to restrict what folks want service meshes to be. So we should be able to add provider specific extensions and bubble them up under SMI for users that want to use more rich feature sets under the hood and not be straddled just to SMI. Okay, so we're going to pivot here and we're going to talk about open service mesh at this point. So open service mesh is just on the right. You've seen this diagram before, but it's just another service mesh implementation that was announced last week. It's being proposed for CNCF donation, and obviously you can come and take a look at the code here. I'll get into what Open Service Mesh is and what it seeks to provide, and then we'll show a demo of Open Service Mesh, which will be a great foray for those who've joining the call and never seen a service mesh in action, because what I'll be showing with OSM is inherent across all these service meshes from Istio to Linkerd. They can all do these things, and they have other features as well. But I think for a common baseline of the things you can expect to have as a user of a service mesh, we can demo that today. The ecosystem that we have here under SMI implementers today, you know, I've mentioned a few of these. So Console, Linkerd, Istio, Rio, we have implementers around the Service Mesh Hub and Meshery. Even the folks at Mesh over there have implementations here of SMI. So as I said, the demo I'm going to show today is actually portable across many of these different service mesh implementations. So OSM itself is designed to be a lightweight, extensible cloud-native service mesh. It's a simple approach in that it's just implementing the SMI APIs, and it's allowing you to have access to secure, out-of-the-box observability, and allow you to manage your microservice environments. OSM also, you know, implements SMI, and we also make sure that if folks want to use Envoy under the hood, and we haven't discussed this, so let me set this up. Most service meshes, indeed all service meshes, ship a control plane and a data plane. The data plane components are typically rolled out as sidecars that sit inside the same pod as your application. And the control plane is responsible for configuring those sidecar proxies to route traffic, whether it's coming onto the cluster, what I would call north-south from an ingress, or east-west, so service to service on the same cluster. So, all this to say, the data plane that OSM actually ships with is Envoy, which is another CNCF project that is extremely popular for these type of workloads, and you see it in a lot of service meshes out there in the ecosystem. So OSM is built on top of Envoy and uses SMI as its main set of APIs to configure Envoy. So some of the principles that we wanted to stick to when working and building OSM was we wanted to be simple to build and contribute to. We wanted it to be effortless to install. We wanted to make sure that you can get up and running if you've never used a service mesh in less than 5 minutes and understand what you're doing and see value in a service mesh. Painless to troubleshoot. Obviously, it's great to have observability, but you want to know that when something goes wrong, you have the means to be able to fix it. So OSM ships with some different debugging endpoints to help you understand what's happening with encryption and things like that, and easy to configure. So again, the star here, I would say the 2 stars are SMI as a standard interface that you can use for that portability, and then Envoy under the hood. OSM itself just configures Envoy using SMI. So I think that shows the value of SMI, that other ecosystem partners can come in and build different implementations of service meshes and use SMI as some of the feature set that they implement. So here are the features that OSM ships with. Traffic shifting, so we can do canary deployments, progressive delivery, end-to-end service-to-service by delivering MTLS on all your connectivity between your services, which is a common request. Access control, we've mentioned that in SMI, debugging and monitoring, certificate management that's pluggable. So many users in the community are looking for, I have my own certificate management system, whether that is HashiCorp Vault or some cloud provided. We wanted to make that pluggable so that you can get certificates from different backends that you already have in your infrastructure. Automatic sidecar injection, that's to get the Envoy proxy located beside your application, and flexible enough. So this is something we haven't talked about. So there's a set of APIs that OSM is talking to configure these Envoy data plane components, and that API is called XDS. And we've also modeled some more complicated things like circuit breaking using Envoy XDS directly in the Kubernetes API. So that's an experimental set of features. Some folks are looking to XDS to be a common abstraction as well for the data plane. So we're looking at how we can model that in Kubernetes and make that your entry point to configuring Envoy. Okay, so that's the features, a pretty baseline set of features there that delivers most users' questions or features that they want from a service mesh platform. Okay, so now we're going to go into a demo. I'm going to send you a link in the chat to this demo, so you'll be able to recreate it. And we're going to go through this demo end to end to show the value of all service meshes, what they can do for you through the lens of OSM. But again, we're going to be configuring it with SMI. So if you follow this demo and you have a different implementation under the hood, that's not OSM, that is fine. But everything will still apply. So this demo is a walkthrough of an application and applying policy through SMI. And we are going to walk it through. So it's going to be nice and slow. I want to make sure that everybody who's first foray into service mesh can understand and follow along, and that I have the opportunity to give everybody the chance to learn. So I will shoot this link out at the bottom in the chat at the end, and you can reproduce this at your own will after this session. But let me kick off the recording, and I apologize for not doing it live, but what we're going to be doing is showing the installed version of OSM. So we have 0.2.0. This is the client binary that can install OSM, and we're performing an install with a single command there, OSM install. This is going to use your kubeconfig and point to a cluster, a Kubernetes cluster, and install all the components required to run OSM. And you can see that that's actually up and running right now in the OSM system namespace with a mesh name of OSM, and this allows you to install many. We can see we have a controller, a Grafana, a Prometheus, and a Zipkin instance, and that's to power many of the features. So what we're going to do now is step through this demo, and don't worry, we're going to give you a set of distributed microservices to walk through and then apply policy to them. So we're going to create a series of namespaces. Again, this is a book buyer set of distributed applications. We're going to create some namespaces. We have a bookstore. We have a book buyer, somebody who would like to buy books from the bookstore. We have a book thief that we're creating a namespace. A book thief is somebody we don't want to have access to the bookstore. And we have a book warehouse, which is this back-end service that the bookstore talks to say, do we have inventory for books? So famous in the service mesh space, the book buyer demo. What we're going to do now is actually say, in those namespaces that we just created in Kubernetes, we want to add these namespaces to have sidecar injection. So we're onboarding them onto OSM to say that any app that gets deployed, please put the sidecar in it because I want it to be on the service mesh. And this allows users to selectively put applications in namespaces onto the mesh or not, depending on how they would like to do that. So we're onboarding using the CLI, those namespaces. Okay, so you can see that we've added the 4 namespaces to be detected and the sidecars will be injected there. Okay, we're just popping over to the demo namespace now, the demo directory, so that we can actually grab the manifest to deploy this bookstore application. And while that's happening, if you are looking in the background there, you can see the distributed application architecture there, the book buyer, book thief, bookstore, and the book warehouse. It's a simple design there, but just to get your head around what's happening, we're actually going to deploy all these things. So we've deployed service account services. We've deployed the end-to-end set of applications. You see some errors at the bottom, and that's only because we manually created the namespaces because I thought that that would make it more clear of how we're actually setting this up. So no need to worry about that. What we're going to do now is actually verify that those applications are up and running and then use SMI to apply policy from everything from access to splitting to metrics. So we're going to walk through that. So we're going to open up now and start, I believe we're going to start the tunnels, so the port forwarding to the backend application. So these applications are running in pods on your Kubernetes cluster. We need to access them from this machine that we're running the demo on. What we're going to use is a Kubernetes port forwarding, which allows wherever that user is accessing that Kubernetes cluster from to present a port on that local host and actually route that traffic through to the backend, which is pretty cool. I know we take it for granted, but it's excellent way to actually test access. And so we have a port forward script here that we ship as part of the demo, and it port forwards to all these applications that we just deployed: book buyer, book thief, bookstore, and book warehouse. So you can see opening up a browser here, and we have different ports. Here is the book buyer. We will go through what's there in a moment. We have the book sold, which is the bookstore v1. We should also have the book thief. And this specific window is the bookstore v2, which we haven't actually deployed yet because we're going to show a traffic split with bookstore v2. So don't worry about that not coming up. And we should also have book thief. So you can see there in the demo, it won't be available at this time. We're going to have access to it later. And we should see the book thief. And these have continuous counters trying to buy books from the bookstore. And only when we enable access will we see those counters incremented. And we're going to use policy to show that the book thief can steal books from the bookstore, and then we can cut the book thief off. So we're going to step through that and demonstrate the power of access policies here. So here's access control policies. And in these policies, we're going to define that the book buyer can have access to the bookstore v1. We're going to apply these, and you can see the YAML snippet there in the background, but we'll apply it and I'll show you the outcome. Then you can look into the documentation after the session to see exactly how we define that. But we've pinned the access to different service accounts and services in different namespaces. So what you can see is we've created a traffic target for the access and a HTTP route group. And what this should do is now program OSM to allow the book buyer access to buy books from the bookstore. So while that's actually being deployed out there, So what's happening under the hood is SMI has read that in, OSM controller has read those things in. It's programming all the Envoy sidecars to allow this traffic. So we can see now, 9 books, that's incrementing. The book thief can't buy any because we haven't given the book thief any access to buy anything. And this demonstrates I want only some services to access the bookstore. But what we're going to do is actually go and edit this policy YAML right now and give the book thief access so that we can demonstrate we can enable policy to allow the book thief access, and we can also disable that. So again, this is explicit in that you define in the Kubernetes resources, custom resources for SMI, exactly what you want to do, and then OSM implements that at the service mesh layer. So here you can see that we have some commented lines out there in blue at the bottom. So we're saying the service account named book thief in the namespace book thief actually has access to bookstore v1, which is up in the spec destination at the top there. So we've made that modification. We're now going to use kube control to apply that to the cluster. Again, we're using Kubernetes native tooling here to configure the service mesh, which is great. You have a single entry point here to configure both Kubernetes and the service mesh. We're going to run a kube control apply here to apply that updated policy manifest, which is going to enable the book thief to steal books from bookstore. So we've applied that. We should see it being reflected in the UI, and the book thief should start to have access to steal books from only bookstore v1, because that's all we've allowed them to steal from. So while that's happening, you can see right now that's being incremented. So now the book thief has access because we've allowed that access, and everything's going through bookstore v1, and here's the backend books sold. So we've demonstrated policy, we've installed OSM, no policy between, we've added policy for the book buyer access to bookstore v1. We've seen that light up. We've also allowed the book thief access to bookstore v1, and we've seen that flow light up as well. So that's access policy in a nutshell. Now we're going to look at splitting traffic. So progressive delivery example. And what we have is we have already deployed bookstore v1. We're going to deploy bookstore v2, and then we're going to route traffic to bookstore v2. I also want to say I'm going to get to questions at the end. I see your questions coming in. Keep them coming. Wonderful. I will go through them at the end. So don't feel like I'm not seeing them. Okay, so we're deploying bookstore v2 right now. So that's been deployed. What we will do is go and make sure that we have access to the UI for bookstore v2 momentarily, and then we'll start to route traffic here. We're just restarting the port forward to make sure it picks up the correct destination. There we go. And then we'll go and over to the browser here and refresh the pages. And this is the first time you'll see bookstore v2. So book buyers still buying books from v1. Bookstore v1 is still there. Book thief is still successfully stealing books because we've allowed them in policy to do that. So we can't say we didn't know. And once this service comes up on the back end, this port forward on port 8082 will have access to bookstore v2. Okay, now we're going to frame the traffic split setup here. Okay, that should come up momentarily. So this is the first time seeing bookstore v2, no book stalled from v2. And we can tell you why that is, because we have a traffic split not defining any traffic to go to bookstore v2. But we're about to change that. Okay, so going back to terminal window here, what we're going to do is actually show you what the traffic split looks like now. And I bet you it will say that 100% of the traffic is going to bookstore v1 because that's the behavior we're seeing. So what we're going to do is use a kube control to describe a traffic split, which is a custom resource called bookstore-split in the namespace bookstore. Now, if you look to the last 3 lines there, backend, service bookstore v1, weight 100. So 100% of the traffic is going to bookstore v1, the service. And what we're going to do is apply a split now. that will route it, I believe, to 100% to V2, and then we'll see that behaved. Okay, so we've applied that. We will go back and describe that traffic split again, and you will see the change in behavior. Okay, so just to model that, we're now seeing book stalled from bookstore V2, and if we go back to describe that traffic split, we will see in those last block under backends, we have 100% of the traffic to V2, 0 to V1. And that is exactly the behavior that we're seeing now. We're seeing all the books sold. If we go back to book buyer here, we should be able to see that also. Okay, and finally, we're going to inspect the dashboard. So it ships with some Grafana dashboards, OSM, to introspect your different traffic patterns, service to service, how the data plane is running itself. So let's go ahead and spin up access to that Grafana dashboard. And we're drawing to the end of the demo now, but there are other introspective tools that you saw earlier. There is Zipkin as well, which will do distributed tracing, which will show you all your dependency graph on RPCs between the services and essentially redraw that architecture diagram that you saw for this demo app. So you have access to observability tools there and dashboards as well to actually monitor your service to service. So we're going to hit Grafana, which we're hitting via a port forward locally that's going through to that cluster, that OSM instance. It's going to ask us to log in here. And we ship a bunch of dashboards inside OSM directly that are pre-installed, so you don't have to worry about them, but you can go and dig into the data. We'll show you just a couple right now. If you have any questions, please go ahead and ask them. I will get to them as best as I can in just a few moments. Okay, so there's some dashboards here, the control plane, the data plane, what's happening. We can see both sets. We're going to take a look at the control plane metrics. We can see different successes, how many connections there are, access, how many requests, any failures, and different traffic attributes. We can also go down and look at the data plane and introspect service to service, pods to service, service to service, workloads to service metrics. So we have some different dynamics here. We're going to pop this one up. You will see that there is no data. The reason is their destination service is not set on the top. So it didn't have context for the data that it needed to pull to fill those out. And what we're looking now is pod to service metrics. So in the namespace bookstore V1 pod, here is the golden metrics that I mentioned coming out of them. So that is an end-to-end demo sharing what SMI can do. So we used SMI to configure OSM. It was OSM under the hood, but it could have been Linkerd. You could do the same demo, run the same demo with any of these things and make it through. Finally, we've just popped up the website, openservicemesh.io, if you want to learn more about that. And let me move to the next slide here. So in summary, there is a lot to navigate when getting into the service mesh space and ecosystem, but we hope with things like SMI being part of the CNCF sandbox community, that folks can start to look at standardized abstractions for service meshes rather than worry about implementations and only worry about them when they need to and have that value in those abstract APIs. If you're interested in service mesh, here are a couple of links. OSM as well, if you want to run up that demo. And as I said, I will pop the link in the chat there as well. It's linked off the main part of the repo, the demo that I did share today. And hopefully that was a good way for everybody to get to understand service meshes, what SMI can provide and what they can do with OSM. So at this point, I would love to open it up for questions. Is Karen, we good to do questions?
Yeah, we are good to do questions. And then just for a really quick reminder, everyone, if you have questions, you will want to submit them to the Q&A tab at the bottom of the screen. So you ready to get started?
I'm ready to go.
All right.
So I'm going to read off the questions. Yeah, go for it.
Okay. I can read them or you can read them.
You go for it, Karen.
Okay, so can we deploy multiple and distinct service meshes on the same cluster shared by different teams using their separate namespaces? If yes, what is the best way to do that?
So The answer is yes, you can do this. I showed OSM. OSM allows you to install a mesh in different namespaces and give it a name, and then you can onboard services to different meshes. It's really service mesh specific. I would be interested to understand why you would do it per team, because then you would have to have some kind of gateway between all the meshes to make sure that they all understand how to connect with each other. I don't know that there's a best way that I would advise folks to do it now. I'll tell you what I'm seeing more of is a single mesh per cluster. And then between clusters, some people are using different mesh tech. So they might have Istio, they might have Linkerd, and then they're actually using different APIs that are out there to connect those things together. I've seen things in Service Mesh Hub to connect two discrete service meshes together and have service A, service B talk to one another. So if you're interested, go check out Service Mesh Hub. But the overhead, I would say, and the tax that you pay is you're spinning up a control plane for each of these discrete service meshes that you're deploying. Now, if resources are an issue, that's just going to be something to consider. So no specific best practices, unfortunately, at this point. But if that's something you're experimenting with, the tooling and the infrastructure should do it. I just would be interested to understand more about why you want to have separate meshes. I'm guessing there's some kind of segregation that you need to have of your traffic. So yeah, next one, Karen.
Yes, second question. Are there samples with north-south traffic, like two services in two different Kubernetes clusters talking to each other?
Yes, so in OSM, we don't ship an ingress controller, but we use ingress to get things on and off OSM specifically. So again, this is service mesh implementation specific. There is gateways in Istio, there's gateways in Linkerd, and they all have documentation on how to do this. So in the case of a single service mesh on a single cluster, ingress is the way that you want to get things on there, and there are different gateways to do that. In the case of north-southbound, as it's been asked in this question, across multiple service meshes, the only way I've seen to do that now is to go and have a look at Service Mesh Hub from the folks at Solo. They actually can tie discrete service meshes together and have a discovery so that service A on cluster A on service mesh A can talk to service B on cluster B in service mesh B and actually have that north-south. I've also seen in Console actually ships gateways, and there's a way, I did a demo a year or so ago where we had two discrete clusters. One was actually running in VMs, the other one was running in Kubernetes, and we created gateways and allowed a service running on VMs access to a pod but via a service name running in Kubernetes. So you can do it. There are some examples out there. It's going to be implementation specific. Service Mesh Hub has some great documentation on multi-service, and the Linkerd folks actually have some great documentation on multi-service and how to do that. That's something I hope we can address in SMI, so I'd love to give you an SMI answer, but I love the innovation that I'm seeing in the ecosystem to solve that problem. Thank you for that question, Luis.
All right, next question. Is it a default deny, which is why the bookstore was not accessible from the book buyer in the beginning, or is it because no routes were created and the services were not able to communicate?
So Ahmad, thank you for this question. In the case of this demo, OSM actually deploys with strict denial by default. You can enable permissive mode, which will allow all by default. So your assertion there and your question is correct. There was no connectivity because we had a default deny in place when we installed OSM. Now this again is implementation specific. Some implementations are allow all, and you need to turn on default deny. So I'd encourage you to look at the documentation. OSM specifically, they implemented with default deny, which meant it didn't light up until I created an access policy. Thank you, great question.
All right, next question. There are 10 questions, okay. Is there a way OSM can do top-based routing and not HTTP-based connection? For example, my app, I see that it's my app. For example, my app needs to connect to Postgres. How can one achieve that?
Yes, so what Fred is asking here, thank you, Fred, is basically layer 4 routing rather than layer 7. SMI can do this. OSM cannot do this now. I've seen it on the roadmap for Linkerd to do layer 4 based routing so that you can have access to discrete protocols that aren't layer 7 like HTTP or gRPC for something like a Postgres and SQL Server. OSM is interested in taking that on. If that's something you need, please go and raise an issue. But I think TCP, MTLS, and a few other things have to fall into place, but that's all doable. So it's dependent on the implementation at the moment as to whether they support that. It's configurable via, you can do TCP-based routing in SMI, so it's enabled there. But if that's something you need today, there should be an implementation, whether it's Linkerd coming down very soon, or they may have it already, or Istio or one of the others. So
cool.
Thank you.
Next question. Does OSM support HA of OSM controller?
It does not currently. Thank you for asking this, Fred. OSM, the team, I was responsible for working on some of it, so I know a little bit of the decision making. It was more to land the experience and prove out what we can do with SMI. HA control plane is something that will come, so it's not there today.
Okay. Someone asked, it's a question about the spec, and it says, it all seems to be in alpha. Does this mean it is not recommended to go into production environments with OSM at the moment?
Yes, so the idea is with SMI to actually prove out and move those APIs as quickly as possible to beta and stable. I would say that it depends on the implementation itself and which pieces you are using. The API itself and the specification doesn't have any guarantees around service availability and uptime. So I can't say don't use it in production. It depends on the implementation. But I would say that if things are in alpha, the idea is there that fields can change, types can change, and the API is subject to change. Being a member of the SMI community, we didn't want to over pivot and move things to beta and stable when we didn't capture a lot of integrations and a lot of user feedback. So I think now that the community is growing and there are more implementations and including OSM, we should be able to solidify these things and move them to beta and stable. The only thing in our way for doing that is making sure that we have user feedback to make sure the APIs are doing what people need.
Cool. Let's see. What are the plans to support multi-cluster scenarios?
So in SMI itself, the conversation has come up a few times. I think what we're seeing happen is folks like Linkerd and Service Mesh Hub are addressing that and building APIs and getting value. And then if the community says, this is a really valuable API, this is a call to action, let's put it in SMI and get other people to implement it so that you have a standard multi-cluster. But I've seen the most traction, and this isn't to say there's more, so apologies if I miss everybody. Linkerd has a great blog on this, and Service Mesh Hub are doing work in this as well. So I'd encourage you to go take a look at those. And if there are APIs you want to be portable across all of them, let's get it in SMI.
Cool. Let's see. How does SMI relate to OPA as an open service, or sorry, open policy agent?
How does SMI relate to OPA? SMI itself is around describing the most common features that the community and users need from service meshes. OPA uses a language, it's a policy engine, which can basically give you a set of constraints. So you pass it a set of constraints, and then you pass it some data, and then it'll go yes or no. So it's a policy engine, whereas SMI is around describing features of a service mesh. So different pieces, how they may combine is there's some projects in Kubernetes that do OPA in Kubernetes. So you could actually restrict what some of those fields have in them using something like Gatekeeper. So orthogonal one is around yes, no on any arbitrary resource, that's OPA. The other, SMI, is a set of specifications to describe features of a service mesh and have them implemented by a control plane.
Excellent. Okay. Would OSM require fundamentally that you have a service mesh deployed?
Yes. So OSM is a service mesh. I'm not sure whether the question was really, would SMI require fundamentally? Okay, so SMI, the specification, requires something to implement it, and that is typically a service mesh. If you have your own homegrown bespoke process internally and you want to use the SMI APIs to maintain some compatibility and portability, you can do that. It's just a custom resource. You write a controller to read that custom resource and act on it. OSM itself is a service mesh. So for this question, the answer is yes.
Great. Let's see. Will SMI grow to cover the ingress domain?
Interesting. The conversations have been had with the Ingress team over on Kubernetes about Ingress v2 and whether it should live in service mesh or Kubernetes. And really, again, what we're trying to do is have the implementers and the users say what they want, and then we can figure out where to put it. But Ingress is one of the biggest pieces that is hard still in service meshes. Some APIs are more developed than others, but I think having a solution that SMI adopts or at least backs, whether that's Ingress v2 and Kubernetes, which is coming along great, or whether something else lives in SMI, I think it would be great to collaborate around one solution to Ingress, have the SMI bit, have the service mesh bits be extensions under that baseline API. So if you have a say, I'd invite you to either, or interested in making your case about one or the other, either come to SMI or go to the Ingress v2 working group under SIG Network in Kubernetes.
Great. Let's see. Okay, so one sec. How much overhead in performance and troubleshooting complexity does using OSM introduce?
So I think service meshes introduce a certain set of complexities. We tried to, with Open Service Mesh, keep that as light as possible. And the way that we did that was not introducing any components that we didn't need to run the core functionality and exposing debug endpoints and APIs. But there is, I don't want to say a service mesh tax. There's something you need to run and that needs to be operated. Whoever is operating that is taking on the burden of that. And there are different implementations which have different operational burdens. What I'm seeing in SMI and the open source community is benchmarking, conformance, and performance tests. I know the Kinvolk folks have done some for Linkerd and other platforms around what is the performance, how does it scale, how does it scale? So, those numbers are out there in the community as well. But I think as a principle of OSM, we wanted to make sure that we kept that tax relatively low. So there is something you need to run, and that something needs to be operational. So that is in turn some kind of burden. How I would quantify that, I don't know to give you any meaningful answer. But great question, thank you.
All right, we have a few minutes left, so I'm going to do maybe 2 questions.
Okay.
Can we scale up or down OSM controllers today?
No. So it's
Okay.
a single controller, no HA. So HA is down the path. So not today.
Oh man, more questions. All right. This might have been during one of your answers, but how about a single service mesh across multiple Kubernetes? Is there such a thing?
You can certainly do that. So you would have the control plane in one cluster, and then the data plane, so all the envoys connecting back to that one control plane, which you need to have the routing set up to do that. What you need to think about, and I only say this because I've done it before, is failure domains. If you lose access to that control plane, you've now lost access to configure that cluster that's on another, that service mesh that's on another cluster because it doesn't have routing access. So just make sure you map your failure domains, and you want to map them vertically all the way up from the hardware all the way up, because what is your failure scenario there and what is your HA scenario? So map your fault tolerance with from your app. What does your app need to have? Am I actually modeling that down in the infrastructure would be my answer.
Okay, last question. How does OSM block access between 2 services by default? Does it use IP tables to achieve it?
So good question. It's actually doing it Envoy itself. So it's Envoy doesn't know how to route traffic things that aren't explicitly told to route traffic to. So the access is done in Envoy itself. So if Envoy doesn't know about a service, it's dropped. So it's done in layer 7, layer 4 to layer 7, depending on how you've got it set up, and it's dropping it actually in Envoy. So it's not doing it in IP tables. It's hitting Envoy, which is that sidecar data plane component of a service mesh, that's making a decision to drop that, and that's not done in IP tables.
All right, let's go ahead and wrap it up. Thank you, Lachie, for a great presentation and Q&A facilitation. That is all the time we have questions for today. Thank you, everyone, for joining us. The webinar recording and slides will be online later today, and we look forward to seeing you all at a future CNCF webinar. Have a great day. Thank you.
Thank you.